Welcome to the linked list course for beginners. In this course, you'll learn everything you need to know about linked lists so that you can pass your data structure and algorithm interviews. By the end of this course, you'll be able to confidently solve common LeetCode problems about linked lists. If you're looking for a clear, concise, and beginner-friendly approach to learning, then you're in the right place. By the way, I'm Alvin. I'm an ex-Google software engineer, and I've helped thousands of people learn algorithms and land their dream job. If you're also trying to prepare for tech interviews too, then you're in the right place. With that out of the way, let's talk about the format of this course. We'll learn about linked lists by solving a series of essential linked list problems. I've chosen these problems because they're foundational to your understanding. As we work through the problems, we'll start at the absolute basics and increase the difficulty slowly so that you never miss a step. We'll take a two-step approach to each problem. First, we'll plan the algorithm on the whiteboard to make sure we visualize everything clearly. There we'll talk about trade-offs and discuss the big O, time and space complexity. Then of course we'll head to my editor, implement the code together, and make sure we pass those test cases. In the video description, I'll provide links to the coding environment for each exercise, so you can follow along and run the tests for yourself. I'll be coding in Python, but you'll be able to follow along in JavaScript, C++, or Java as well. All right, without any more delay, let's head to the whiteboard so I can introduce you to the data structure of linked lists. The first thing we'll need to know is that a linked list is a type of data structure, right? So it organizes data, and in particular, a linked list is made up of many nodes. So as our first checkpoint here, we need to first understand what a node is. You can think of a node as just a container for some data. So when we conceptually visualize nodes, we really think of them as some circles that I can put some data inside. Here I'll put a letter or character inside of my node, but of course you can store any data you like. It could be strings, numbers, booleans, or even other objects, right? And I'm saying that a linked list contains many nodes. So let's say I had a bunch of nodes. And they can all contain different pieces of data. So I have the characters A, B, C, D stored in different nodes over here. And if I wanted to make these nodes comprise a linked list, then what I need to do is add some links. In other words, if I have a node like A, I can make it point to the next node in the data set. That is, A points to B, right? I can also say that B points to C and C points to D, right? And the term we actually like to use for this is really saying that A's next is B, right? It's going to be very common linked list terminology and a pattern we're definitely going to see in the code later on. And now you can already see why you call this data structure a linked list, right? I have a bunch of nodes linked together. An important thing to note here is about the last node D, right? D is the last node in our linked list. And so under the hood, we can really represent it being the last node by it having its next pointer pointing to nothing. Or more programmatically, we can have its next set to null, right? The null pointer in whatever your language of choice is. So sometimes during this course, I'm going to explicitly choose to draw out the null node or the null reference, just so we can build some very robust code. All right, now that we know what a linked list looks like, I want to introduce some other terminology that you're going to hear, right? So when we refer to the very, very first node of a linked list, that is the A node in this diagram, I consider that the head, right? It's a very common term. In a similar way, we can refer to the very last node in a linked list as the tail. Right? So if you hear those words in problems, we're referring to the first node and the very last node respectively, right? And if you think about it, because I have this sense of different nodes and, a first node and a second node, we can think of a linked list as an ordered data structure. In other words, if I started at the head of the linked list, I can just look at this node's next pointer and I can go to the B node. So I can just move to the right. And once I'm at the B node, I can see that B has a next that goes to the C node and the C node goes to the D node. And the D node goes to the null node, which must mean that I'm at the end of the linked list. So that's a very, very key characteristic about a linked list, right? A nice property to leverage about a linked list is that it's an inherently ordered data structure, right? If you want to refer to like the positions of these nodes, and we do that programmer thing of starting at 0, I can see that the head has a position of 0, B has a position of 1, and then we just go sequentially throughout, right? So there are 4 nodes within this linked list. I can see that the position of the head is 0, and the position of the tail is 3. And so far, we're probably not seeing the full value of a linked list. Like, when would this data structure have some real utility over other data structures that we know about? In other words, you're probably wondering how a linked list compares to an array, because an array is also an ordered data structure. So let's do that comparison right now. So here I have my linked list up top, And if I wanted to represent, a similar data structure, but in an array form, it would look something like this, right? I have an array in memory, and I know that that array has some indices, right? So there's a really clear analogy here. I know that the indices of an array correspond to the positions of the nodes of a linked list, right? And obviously my linked list is made of many nodes, whereas my array has many elements. The most important difference between an array and a linked list is that an array must be stored contiguously in memory. That means all of your elements in an array are going to be stored like right next to each other in your computer's memory. And that has a lot of consequences in the runtime of different operations across your array, right? So let's say right now I wanted to step through a scenario. Let's say I had the goal of inserting a new element q at index 2 of my array. And the key specification here is I want to insert q at position 2. I don't want to overwrite the current element at position 2, right? So at the start of this operation, I have 4 elements in my array, A, B, C, D. After I do my insertion of q, I should have 5 elements in my array, and they should go A, B, Q, C, D, right? Because I'm inserting some new element at index 2. So how would this algorithm run at a high level in an array? Well, typically, all we would need to do is obviously find the index 2, which is right here. And I know that this is where I need to put the new q element. But I can't just overwrite this value of c because I want to do an insertion, not an overwrite. And so what happens under the hood in your programming language when you perform this insertion operation? Well, we hope that there's still some empty space in the array, and it should occur after d, right? Assuming that there's still space in this array, I would need to shift all of the elements to the right over by 1 index. In other words, I need to put D to the right. I need to put C over 1 position to the right. And now I have perfect room to add this Q at index 2, right? And of course, now D would be occupying a new index of 4 logically. But the important step we took here was to actually insert somewhere in the middle of an array. That could mean that you need to shift over a bunch of different elements in your array, right? So in this very small example, I only had to move over 2 elements of C and D. But let's say you had a very long array and there were, 1,000 elements after your insertion index. You would have to shift all of them over one by one. And that is a relatively costly and slow operation for such a simple move of inserting Q, right? So we say that when we insert into an array, that does have an O of n insertion time, right? In the worst case, if you insert at index 0 of an array, that is you're inserting a very first new element, you would have to shift everything over by 1 index in the array. And since there are n elements in the array, you're doing n different shifts. Awesome. Now let's compare that to a similar insertion operation for our linked list. So let's say I still wanted to insert the value of q at position 2 of my linked list. Well, that means I need to create a new node in memory. And what's great about a linked list is it is not required that the nodes are contiguous in memory. In other words, we can have these like nodes exist anywhere in the space of our computer's memory addressing. And that's kind of a very low-level statement, but the consequence of this is I don't need to do any shifting when I perform this insertion. In other words, how does that work? Well, if I want Q to become position 2 of my linked list, now that I've created the new Q node, I just need to adjust B's next pointer. So I'm going to look at node B and reset its next pointer to point at Q. Then I set Q's next pointer to point at C. And with those small changes, I've actually changed the logical order of nodes within my linked list. It would now be this, right? Q occupies position 2, C occupies position 3, and so on. And what's really great about this is, let's say that there were many nodes after my insertion position. Let's say there were 1,000 nodes. Well, I wouldn't have to actually modify all 1,000 nodes that came after my insertion point. I just need to change about 2 pointers every single time. And because that's a constant number of operations, I will say that a linked list insertion, if we write it correctly, will be constant O of 1 time. So here we see a very tangible difference between our linked list data structure and our array data structure. And there are many more different pros and cons between these two, but for now we'll leave it at that and we can chat more about them as we go throughout the course. I'm sure it's going to come up. But what I want to do for now is talk about the core a linked list algorithm. And that's just traversing through a linked list. In other words, how can we just touch and process every node within a linked list? Well, the important thing to know is if you wanted to like give a linked list to someone, or in other words, programmatically pass a linked list into a function, you really only need to pass a reference to the head node of a linked list. Because if I give you the head node of a linked list, by accessing the next property of every node, you could have access to the full sequential list, right? And so to actually implement a traversal algorithm on a linked list, we just need a handful of variables. Most importantly, we need like a current variable, a current reference to look at the current node of the linked list we're iterating through, right? So if I have this current node of A and I want it to go to the next node, I can just look at current.next, right? Or something similar in the programming language of your choice. And I can just set current equal to current.next. Then I would be at the B node. And B also has a next. So I do that again. I'm at the C node. And I can just keep continuing this process, right? Assigning current equal to current.next. Until at some point, once I'm at roughly the tail, current would be D. And so current.next would be this null node or this null reference. And if I set current equal to next, I'll be right at null. And that can be a perfect condition I can catch. In other words, we can stop the algorithm when current is equal to null. We know that at that point we would have visited every node of the linked list. So as I went through this high-level trace, I was kind of speaking upon this algorithm as if it was an iterative solution, and I'll also show you how you can solve this one recursively. It's really the same line of thinking. At this point, I would want to actually hop into some code so we can see the nuts and bolts implementation of a linked list, as well as the core traversal algorithm through a linked list. At this point, we're done planning and ready to code things up. In this next section, I'm going to be coding up the algorithm we just spoke about step by step. You should follow along and implement the code with me. I'll leave a link in the video description to a coding environment where you can jump right in and follow along. Be sure to find the right timestamp and open that link in a new browser tab. Hey programmers, Alvin here. Right now I want to walk through a Python implementation of how we can implement a basic linked list traversal algorithm. But first, what I'll need to do is actually give myself a linked list to perform the algorithm on. What I'll do to start is just create a node class. So using some Python class syntax, create class node. And in the constructor, or the initialize method, for this class, I just need a single argument. I'll call it the value. If you're familiar with Python classes, you'll always need to take in a reference to the self as well. Cool. At this point, I just want to assign this value as a property. This is going to be the stored value within my node. I know that every node is also going to need a next property that points to the next node in the linked list. So I'll do self.next. I'm going to just initialize that to be none. So by default, nodes have no next. Awesome. And I'll just create a pretty hard-coded linked list. That way we can just jump into the algorithm here. And so I'll create a variable called A. I'm going to store inside of it a node. I'm going to give it a value. I can put anything as the value. I'll just use some uppercase characters here. And I'll create a few different nodes. I'll do A, B, as well as C, and finally a D. And at this point, what I also want to do is now join these nodes. I need to set their next pointers. So this is pretty easy to do. I'll just say A.next equals B, and then B.next equals C, and of course C.next equals D. And there I have my very first linked list. Conceptually, it looks like this, right? I have A points to B, and then B points to C, and then C points to D. D's next is actually going to be none here, so I'll just represent it like this, right? I'll just say none. Awesome. So that's my linked list. Now let's write our traversal algorithm to just print out every value within our linked list. So I'm going to build a function to do this, and I'll just call it print list. And I'll just take in the head of a linked list. I'll recall that the head of a linked list is going to be the very first node. So here, the A node would be the head of the linked list. In other words, a valid call to this function would be printlist, and you pass in a node, so the A reference over here. If I wanted to implement this function, what I'll want to do is start by attacking this one iteratively. This is going to be a very, very core linked list algorithm. What I'll need to do is maintain a variable that points to my current node. I'll just call it current. I'm going to initialize it to be the head node. What I want to do then is set up a while loop that keeps iterating while the current is not none. Right? So while the current variable is not none, I'm going to keep running the algorithm. All that means is I need to print out the current node's value, right? If current is a instance of node, and I know that every node has a val, so I need to fix that over here. It should just be val. And from that point, what I also want to do is now update my reference for current. I already consumed the current node, so now I just need to look at the next node. So I just set current equal to current.next. Right? Then I go to another iteration of this while loop, and I keep running this while loop while current is not equal to none. And that'll be the complete implementation for an iterative print list function. Let's go ahead and give this a manual run. We should see all of our values printed out in order, which is perfect, right? So if I do a quick little trace through this algorithm, I just need to track what my key variables are. Here, really just the current variable changes over time. I know that the current variable starts at the head node of A, so I'll use cur to represent that. All right, notice how I'm aligning it vertically here. So on the first iteration, I set current equal to A, the A node. Then I check, is the A node not none? And that's true. So what I do is I print out current val. That means I print out the A over here. At this point, I set current equal to current.next. Well, if this is current, that is the A node is current, then obviously current.next is going to be this B node, right? And when I take that current.next, I'm going to assign it into the current variable. So that has the effect of just moving this cur pointer to the right. And obviously, if my current is B, that means the new current.next is going to be C, right? So this logic continues. I'm back at the top of my while loop, and I check, is current not none? And that's still true, right? Because B is not equal to none. So I print out B over here, and then I set current equal to current.next. So now current points to C. This condition is true once again, so I print out the current value of C in my terminal over here. And of course, we set current equal to current.next. So at this point, my cur is equal to D, and this while loop condition is still true, right? D is not none, and so I print out the D node. And at this point, I would actually set current equal to a current.next, so cur now is pointing to this none. And when I get to the top of my while loop, once again, I check, is none not none? And that's actually false, so I exit my loop, right? Then I finish my entire traversal. Notice that the way I've written this condition here for my while loop, it will actually be the case that when I terminate the algorithm, that means that current is exactly on a none, which is good to go. And so that was an iterative solution to our linked list traversal algorithm. Let me show you how you can also implement this one pretty easily with some recursion. So we'll define print list once again. And if I want to actually solve this one recursively, I know that means I need a base case and a recursive case, right? So my base case is going to be about a linked list that is very small. So I ask myself, like, what's the smallest linked list I can ever have? Well, the smallest linked list would be the empty linked list. That is the linked list with 0 nodes. And so I want to catch that explicitly here. I'm going to check, right? If the head is none, that means I have an empty linked list. So if the head is none, then I'm just going to return, right? There's nothing to print inside of that empty linked list. So that's my base case. But in the recursive case, that means that my head is not none, so it must be an actual node. If it's an actual node, I know every node has a val inside that I need to print. So I'll start by just saying print head.val, right? And at this point, I printed out my current head's value. I need to print out the rest of the nodes in the linked list. So that just means I make my recursive call here, call print list, and pass in head.next, right? That way, when I evaluate this recursive call, I'm back in another stack frame, right? So I'm calling print list, and head is now going to be processed with really the next node sequentially in the list. And that's going to be all we actually need to implement this one recursively. So let's give that another run. Clear out my terminal here. We should get the same output, right? Just printing out every value in order. And the trace here is really the same. You're just kind of thinking about it recursively now, and especially noticing that we have this head argument that changes over time, right? So if I'm tracing it, I know at the very start I call it print list, and now this like head argument starts at the A node over here, right? And I check, is this A node none? And that's false. So I continue to the recursive case. I print out my current head's value. So I print out the character A, and then I make a recursive call on head.next. And of course, that means I move this head now over to the B node. And now I'm in a recursive call where the head is B. And I check this base case. It's false, right? The head is not none. So of course, I print out B, and then I make a recursive call upon the C node. And this process continues. Let's say we get to the point where our head is none, then of course this conditional, this base case is true, so I just return and that ends my recursion. Alright, so that was our warm-up into linked lists for all of our Python programmers. In the next few tasks, I'm going to give you some problems where you can actually implement these core algorithms on your own. Alright, now that we know how to implement a basic linked list traversal, let's head back to the whiteboard and discuss our first real linked list interview problem. Hey programmers, Alvin here. Right now I want to go over an approach for this linked list values problem. So we'll hop right in right here. In this problem, you're going to be given the head node of a linked list. What we want to do is return an array containing all of the values within the nodes of that linked list. And we should do it in order. Bear in mind in this problem, we're given a singly linked list, which means that every node has a pointer to the next node in the linked list. We know that the last node of the linked list would have a next pointer that points to null. With that being said, how can we go about solving this one? Well, this problem is we're just going to have to force you to implement a really core linked list pattern. That is, just traversing through a linked list in order. And so we'll start by attacking this one maybe with an iterative description. So let's say we started from ground zero, right? So we want to create our values array. And to the side, we can just initialize values to be an empty collection. And to implement this core pattern of just traversing through a linked list, we're going to need a variable or just a pointer. And we're going to start at the head of the linked list, right? Bear in mind that our function only takes in the head, but I know the head is like the ultimate starting point of the linked list, and eventually I could access everything throughout the entire list. So I'm going to set my current equal to the head, and what I can do off the bat is just check current's value and add it to my running collection. So I have the A value inside of values now. And since I have access to the current node, I know that if I access its next property, I would have access to the next node of B. So what I can do is set current equal to current.next, basically just moving my pointer to the next node like this. Same thing as before, I can add my current value into the collection. And I'll just proceed in this way, right? Same thing for C, set current equal to current next. And things get interesting once we approach the tail of this linked list. So I'm currently at the D node, and I go ahead and add that value into my values list. What we'll have to do now is consider the scenario when it's appropriate to actually stop our traversal. Well, bear in mind that D's next actually points to null. So maybe I'll draw that explicitly just for this drawing. So D's next is just pointing to null, which means if I continued this algorithm in the general sense, so I set current equal to current next, that means my current pointer now points to null. And I think that would be a perfect stopping condition, right? So once current is null, we know that we've hit the end of our linked list, and so we're totally done. And if you look at the order of our values, it is indeed the correct order, right? What can we say about the complexity of this algorithm? Well, if we say that n is just the number of nodes in this linked list, then the time complexity is going to be O of n, right? Because we're just really iterating through every node once. And our space complexity, if we consider the output array, it would just be also linear in the number of nodes over here. And so I'll tell you what, this looks like a pretty good strategy that we can go ahead and implement. We'll implement it in two ways. First, I'll show you the iterative version and also show you how to implement this one recursively. Really, both the iterative and the recursive code use the same sort of mechanisms. So I'll see you in the walkthrough video. Now that we planned out the solution for this problem on the whiteboard, let's head to my editor so we can code things up. Like before, you should follow along and code with me. I'll leave a link in the video description to a coding environment where you can code things up and even execute the test cases for the problem. So go on down to the video description and click on the link. I'll have it labeled with the relevant timestamp. Hey programmers, Alvin here. Right now I want to go over a Python solution for this linked list values problem. So we'll jump right in, and I think we'll start by implementing the iterative solution for this. And we said that the key to victory here was to use a variable to track your current node. So I'll start by creating that variable, and I do want to initialize it to be the head node. Then from there, we keep running our algorithm while current is not equal to none. We know in this problem, our eventual goal is to return a list of all of the node values. So I'll create that collection over here. I'll just say values and make it an empty list. And then as we iterate through all of the nodes, for the current node, I'll take its values. So I'll take current.val, right? Every instance of node has a .val property, and I'm going to append that into the values list. So values.append current.val. And then from there, to progress to the next node in the linked list, all I do is set current equal to current.next, right? Notice that here we take the right-hand side and we store it into the left-hand variable name, really just shifting our point of view. I know eventually, once I get toward the end of my linked list, let's say that right now our current is D. When we set current equal to current next, we would be setting our current equal to none. And that would actually exit this while loop, at which point I just want to return the values list. Awesome, so we'll give this a test run, see what we get. Nice, and there we have a solution for this one. All right, so let's go ahead and also take a look at how we can implement this one recursively. It's very, very similar code. So what I would do here is, of course, define the same function. And I would actually split this up into two functions. I would have my main function just set up the list. And then I'd actually return the list at the end. Then I'll create like a helper function to actually do the recursion. And that's to help me get a really nice runtime out of this one, right? And so what I'll do is create some helper function. I'll call it maybe fill values. It's going to be recursive, so it's going to take in the head of the linked list and also a reference to the values list. And so here I would be passing the values list by reference, so my fill values function should actually mutate that variable. So over here I'll say define fill values. And what I should do here is basically just try to translate this while loop into its like recursive version. And so basically I'll take the condition and translate that into a base case. So when should I stop? Well, I should stop if head is null. So say if head is none, then I can just return. Otherwise, I know head is not none, so it must be a node that contains some value. I'm going to take that value and append it into the values list. So I should have taken that in as an argument here, so values. And I can say values.append head.val. And then from there, I just need to traverse to the next node of the linked list, so just call recursively, right, fill values on head.next. Cool. So it basically translated every pattern from the iterative code into its recursive form. The reason I have this split up into multiple functions is so that I can continually recursively add to a single existing values list, right? So I don't have to create like copies of multiple lists, because that would actually slow down my runtime. So this would actually still have O of n time and O of n space. Let's go ahead and run it to make sure that it works. And I think at this point we also have the recursive version under our belts. Looks like I have a little typo here. Of course I need to pass in values over here as well, so I'll give that another run. Perfect, and here's a recursive solution. So I recommend that you actually practice coding up both of these solutions. It's really important that you have both implementations under your belt, because depending on the type of problem that we're going to solve in the future, you may find either of these more useful than the other. So with that, practice this, and I'll catch you in the next one. So we just solved our first linked list problem. We have many more linked list problems to solve, but the best part is they'll all build on top of this essential algorithm. If you've been enjoying this course so far, I think you'll enjoy my complete data structure and algorithms course at structy.net. This linked list material you've been working through is actually pulled directly from the course. There you can learn about all of the data structure and algorithm topics you need to pass your tech interviews, from trees to graphs to dynamic programming and more. The best part is that I've designed the course so that it builds up your understanding step by step to make sure that you really master the concepts. I'll teach you all of the techniques I used to land my job at Google. Here's what a user from our Discord said about the course. You can try the course for free today. I'll leave a link down in the video description if you're interested. Now let's head back to the whiteboard and talk about the next linked list problem. Hey programmers, welcome back. Right now I want to go over an approach we can use for this sum list problem. So in this problem, we're going to be given a singly linked list containing numbers as the values. What you want to do is return the total sum of all the values in the linked list. So for this particular input, we should return a total sum of 20. And so how can we go about solving this? Really just reviewing a core linked list pattern, right? All you have to do here is just traverse in order through the linked list, and you can accumulate a sum. So let's say we start from the beginning. If we initialize some sum variable to 0, we can also just use a pointer that starts at the head of our linked list. And what we can do is we can take current value and add it into our sum, just updating the sum. So I take my current value of 2, add it to my sum. My total sum is right now 2. Then I can set current equal to current next. I can add this 8 into my sum, getting 10. Next iteration, I can add my 3 into the sum, getting 13. Next iteration, I can add 7 into the sum, getting 20. Right? And I know that technically 7 does have a next pointer, and it does point to null. So let's say I drew that out explicitly. What I can do at this point is actually continue my algorithm, and I can make the stopping condition when my current points to null, right? So in general, we can code this up by saying a loop like, while current is not null. If we talk about the complexity of this algorithm, it's pretty straightforward. We're technically just iterating through every node. So if n is a number of nodes, we have O of n time, roughly one iteration for every node. And then our space complexity here is actually O of 1 if we do this iteratively, right? The only variables we need to maintain are really just current and also the sum variable. And we're just going to store some primitive values in there. So we have a nice constant space solution over here. So the iterative is really straightforward. Just for complete understanding, how can we solve this one recursively? Well, if you solve it recursively, that means you have to call your function many times. And we start with a top level call on the head node of 2. And what this should do is really just call upon the next node, right? So I should call upon head.next. So that should give me a call to this 8 node. And that should call upon the 3 node. And that should call upon the 7 node. And finally, the 7 node should actually call upon its next, which would be the null node. And that will actually act as my base case. I think it's a really great one. What I can do with this base case, right? If my node is null, then I can just return 0. Right? Think of null as if it's an empty linked list. What is the total sum of an empty list? Well, that would definitely be 0. So I'm going to plug in this return value, right? So I'm saying this call to the null node is going to return 0. When we say return, that means return to your caller. So this 0 would actually be returned into the 7 node. And what the 7 node should do is add its current value, right, its own value, into that number, giving 7. And then that returns up the stack. At this point, I return back to the 3 node. 3 can add its value with that 7, giving 10. I'm just returning that up. 8 can do the same, giving me 18. And finally, 2 can add itself into that return value, giving us 20. And that would be the correct answer, right? So there are plenty of ways to implement this one. If we solve it recursively, we're definitely going to have one call for every node within our linked list. So that would be O of n time. And the space complexity would actually be a little more than our iterative. We would have O of n space here because of the call stack, right? Typically, when we analyze our recursive functions, we should include the space utilized for making these recursive function calls, right? So O of n over here. Notice that when we bottom out at our base case, we would have, roughly like 4 or 5 things on the call stack. All right, so those are the 2 strategies I think will code up, and I'll catch you in the walkthrough video. Hey programmers, welcome back. Right now I want to show you a solution in Python for this sum list problem. So I'll jump right in, and I think we'll start with the iterative version. I'll show you also the recursive version later on. And so to solve this one, I do want to accumulate a total sum. So I'll create that variable, just call it total sum, set it equal to 0. I know by the end of my function, I'm going to return that total sum number. And then I need to lay down the foundation for my just classic linked list traversal. So I need some variable, I'll call it current, initialize it to the head. And I know that the main boilerplate I need is to iterate while current is not none. And the important code I need is to set current equal to current not next. So just this code, basically the variable of current and also this while loop, is a really, really core pattern for linked lists. And then from there, how do I actually want to utilize my current node's value? Well, all I want to do is just take current.val, and I should just really take it and add it to total sum. Just increment it. So I'll say total sum plus equals current val. This should be a fine solution, nothing fancy at all. So we'll give it a shot. A few things I do want to emphasize about this implementation. Typically for my linked list problems, I always like to write my iterative code just like this. A common mistake I've seen students make in the past is to sometimes preemptively write logic about current next. In other words, it's not going to be too useful to write patterns like this, right? Current.next.val. Instead of looking ahead in the linked list, you should only really worry about your current node itself, because depending on the length of the actual linked list, you may not actually know if there's a valid next node. So always try to stay very present in your code, right? That's why my base case is about current and not current.next, right? And that's why when I add the value, I'm not saying current.next.value, right? It's about staying very present. That way you don't make any assumptions about the length of your input list. So this is the very classic iterative version. Now let me show you how you can do this one recursively. I think the recursive solution is really elegant. And so we'll start with our base case. We always know our base case is going to be when head is none. And so when head is none, I like to think about my base cases as if they're their own inputs, right? So if head is none, that kind of means that I have an empty linked list. What's the total sum of a empty linked list? Well, it's definitely just 0. That's my base case. And I know I'm going to need to recurse here, so I'll say sum list. And I'll pass along the next node in the sequence, right? Head.next. I know that if head.next is none, then I'll just get back 0. But if it's not none, then I need to do some computation, right? I know this call, it's going to return to me the sum of the remainder of the linked list, right? With everything else in the linked list. I'm going to take that and add it with my value, right? My value is head.val. And I would just return that quantity. This is really all we'll need for this recursive sum list solution. So let's give that a go. I should get the same behavior. Do bear in mind, when it comes to the complexity of this, time complexity is going to be the same as our iterative, right? It's going to be O of n, where n is the number of nodes, because we make a recursive call for every single node. And the space complexity of this is actually also going to be O of n because of all of the stack frames we add to the call stack, right? To even perform any recursion, your programming runtime is going to need to actually add that information onto the call stack. And so we will consider this linear time and space. All right, programmers, so before you hop into the next problem, I want you to practice both the recursive and iterative flavors of this, and I'll catch you in the next one. Hey programmers, welcome back. Right now I want to go over the approach we can use for this linked list find problem. And I'll show you 2 ways to solve this one. So in this problem, we're going to be taking in a linked list as input, and we also have a target value. What we want to do is return true or false whether or not the target value is contained within the linked list. So for this particular example, if I'm asking you for a target of C, you should return true because C is definitely within the linked list. In another scenario, let's say I gave you a target of G. In that scenario, you would just return false because G is not a value of this linked list. To solve this one, we're just going to use our classic linked list traversal algorithm. So we'll step through it as if we're looking for C. So in the long run, we expect to give back a true here. Well, I know that they're going to give me the head of the linked list as input, and I'll create a current variable that points to the head node. Of course, I'm going to progressively update this current variable to be the next node over time, right? So what I can do is whenever I'm situated at some current node, I can check if my current's value is equal to my target value. So right now I would check, is A equal to C? It's not, and so I should keep looking through the linked list. I know that current also has a next property, so I'll update current to be current.next. And then I check, is B equal to C? It's not, so I keep going. And finally, I can hit a point where I see that my current value of C is equal to my target value of C. And so I can just do an early return true, right? Once I find a match within my linked list, I can just return my final answer. Now let's say we had the opposite scenario. Let's say that my target was G. We're going to start the algorithm in the same way. We start at current, and when we keep looking through the linked list, and we set current equal to current next, eventually we know that current is going to be equal to null, which sort of signifies that we've hit the very end of our linked list, right? And at this point, once we finish iterating through the entire linked list, we know that we didn't see the target value because we were checking the entire way through. And so at this point, we can do return false. This is a really practical programming pattern, right? Where we check some conditional inside of a loop, and if we find something we're looking for, we'll return true early. Then afterwards, after our loop's done running, we'll return false late. When we talk about this iterative strategy, we know that if n is the number of nodes, we're just going to iterate through every node of the linked list. So we would have a runtime of O of n. And our space complexity here would just be O of 1 because we're just using a constant number of variables. So that was the iterative solution. How can you also solve this one recursively? So let's say we were looking for the target of C and we had a more recursive point of view. So we know we're going to make a top level call on the head node of our linked list, and I can just think about some base cases to use here, right? And I know I need 2 base cases, right? One that can return true and another that can return false. So for my first base case, I can just simply check, all right, if my head's value is equal to my target, then just return true. And in the opposite scenario, let's say that my head is null, then I should just return false. What I always try to do with my recursive code is to think about my base cases as if they're their own valid inputs. So in particular for base case number 2, if head is null, then that kind of represents the empty linked list. If my linked list is empty, then I can return false because I definitely can't find the target within an empty linked list. So how would this run for our current input of target C? Well, I would check, all right, is A my target? It's not, so I make a recursive call upon B. Same thing, right? It's not. Make another call upon C. And at this point, I see that my current head's value is equal to my target. And so this node is going to return the Boolean true. And I know that this return value is going to return back to its caller of B. And then B is going to pass it back up to A. And of course, A returns it to the very, very top level call. Let's say we had a scenario where our target was not found within the linked list like G, then we can see the other base case fire at the very end, right? So I know I'm going to make a call on A calls B calls C, I still don't find the value, C calls D, and finally, when D looks at its next, it's going to pass along null, right? Because D's next is technically null. And at this point, I have just hit base case number 2, so I can return false. And like before, I return these values up the call stack. When we talk about the complexity of this recursive algorithm, we can say that n is a number of nodes. We're definitely going to have O of n runtime because we make a call for every node of the linked list, but we also have O of n space, right? Because each of those calls, by the time we bottom out at a base case, we would have to store those on the call stack. We know that the worst case scenario is if our target is not found within the linked list. That being said, I think these are 2 fair algorithms to go ahead and implement, so give it a shot on your own, and if you get stuck, I'll catch you in the walkthrough videos. See you there. Hey programmers, Alvin here. Right now I want to go over a Python solution for this linked list find problem. So we'll jump right in. Hopefully you watched the approach video for this, and I'll start by showing you the iterative solution for this. It's really straightforward. So we'll start with just our pointer variable. So we'll say current equal head, and I want to keep iterating while my current is not none. And I know that if I just want to progressively hit the different nodes in sequence of my linked list, I can just set current equal to current.next. So this is a super duper core pattern when it comes to singly linked lists. And now how do I work in my problem specific logic here? Well, as I check every node of the linked list, I want to see if its value, so if current.val is equal to my target. If I'm at a current node whose value is the same as target, then I just found what I'm looking for, so simply return true, just like this. So I have a way to return true. That begs the question, where should I return false? And the trick is to return false only after the while loop, right? So return false over here. We know that we should only return false after we check the entire linked list and don't find what we're looking for. A common mistake that you should avoid is just writing an else return false. Sometimes this might be your instinct, right, to just say if then return true, else then return false, but that's not going to work out over here, because if you don't find the value in the very first node, then you just automatically return false without even looking at the rest of the nodes within the linked list. So instead, you only want to return false after the while loop. So let's give this a shot. Nice, and there we have a solution for a linked list find. So while we're here, let's also bang out the recursive version of this. Like we mentioned in the approach video, the recursion is going to use 2 base cases, right? One to return true and another to return false. So let's start by checking if head is equal to none. So if head is none, then I'll just return false. So here I like to think about this base case as capturing the scenario when my linked list is empty, right? I can't possibly find the target within an empty linked list, and so I return false. Another base case we need is one that returns true. And I should return true if head.val is equal to my target. So I just found the thing I'm looking for, so return true. So these are going to be our 2 base cases. Important thing I want to bring up over here is this is actually the correct order. You should lay these out. What you don't want to do is actually write this code, right? This would actually fail if head is none, because the first thing I check is if none.val And that would throw an error because I can't check none.val. So instead, we should guard immediately by checking if head is none. Nice. And so in the recursive case, let's say that neither of these conditions are met. So our head is not none and our head val is not equal to the target. Well, then I need to check the remainder of the linked list. So I can just call recursively, right? Here's the recursive part. And I pass along the next node in the linked list, so head.next. I should also specify a target here. The target never changes, so just pass that target along just for the sake of the comparisons down the line. Now I'll think about what type this function call returns. I know it's going to give me back a Boolean, right? True or false, whether or not I can find the target within the next node and the remainder of the linked list. So whatever Boolean I get back here, I just want to return that. Nice, and this would return the answer all the way back up the call stack. So let's give this a run. Pretty concise recursion. Awesome, so here's the recursive version. And so they're both good solutions. Do bear in mind that when it comes to the complexity comparison between these two, they both have an O of n runtime. But in the case of the iterative one, it actually uses a constant amount of space, whereas the recursive one uses a linear amount of space because of adding all of the calls to the call stack. That being said, I want you to understand and practice both of these solutions, and I'll catch you in the next problem. See you there. Hey programmers, Alvin here. Right now I want to go over the approach we can use for this get node value problem. So in this problem, we're going to take in a linked list, and what we want to do is also accept an index as input. And what we want to do is really return the node's value at that given index, and we will start counting our indices at 0. In other words, we'll consider the head of our linked list as having index 0. So for this particular example, if I asked you for index 2 of this linked list, you should return the value of the C node, right? So just return the value C. And of course, I could be giving you any particular index as input. So what this question asks is pretty straightforward, but how can we go about solving this one? And so what we can do here is a basic counting algorithm. So we know we want to return the node's value who has index 2. So when we initialize our current pointer to be the head of the linked list, we'll initialize our count to 0. And then from here, it's just our classic logic, right? I know I can set current equal to current.next. And when I do that, I'll also increment my count. So now count is 1. Basically, I have tracked the index of my current node that I'm iterating through. Next iteration, when current goes to C, and of course I increment my count to 2. At this point, I can see that my target index and my count are equal, and so I can just return the value within that particular node. If I think about this strategy, it's pretty straightforward in that if n is the number of nodes, the time complexity is simply O of n, right? Because in the worst case, we just have to traverse through the entire linked list. We can also say that the space complexity for this is constant because we're just tracking some simple number variables. So that's how you can solve this one iteratively. How can you also think of this one recursively though? So let's reframe our point of view here. Let's say that we were forced to solve this one recursively, and we know we still want to find the value at index 2. And when I make a call, I know that the top level caller is going to pass along the head of the linked list, so the A node, and also their target index of 2. I can use my classic recursive linked list traversal algorithm. So I make a recursive call on my next node. When I make the recursive call on the next node, what I should also do is pass along the index, but decrease it by 1. So now I'm able to see that, hey, this current node of B has index 1. And if I keep doing this, next iteration, I call upon my next node of C, and I also decrement my index down to 0. Once my index is at 0, that basically means that I want to return this very node, right? So if index is equal to 0, we'll return node.value. That would be our base case. And once we return that value, I know that I'm going to return back up the stack. So the C value returns to its caller, and so on and so forth. Very classic recursive code. So this looks like a nice recursive algorithm. When we analyze the complexity of this, we're going to see that the time complexity is still linear, and the space complexity is actually also linear here. Here we incur a little more space complexity because we're going to be storing every call upon the call stack. So what I want you to do is, on your own, try to give it a shot and implement both the recursive and iterative solutions for this problem. And if you get stuck, I'll catch you in the walkthrough videos. Hey programmers, Alvin here. Right now I want to go over a Python solution you can use for this get node value problem. So hopefully you watched the approach video already, because we're going to jump right in.
And I think this time around, I'll start off with the recursive version. So one base case I always need is if my head is none, right? So that basically means if I hit the very end of my linked list, or if I just have an empty linked list. In either scenario, if my head is none, then you can just return none. That's actually something stated explicitly in the problem, right? They tell us, all right, if there is no node at the given index, then you can just return none. So an example that would describe that would be this one, right? Here my input linked list only contains 4 nodes, but they ask me for the node at index 7, which definitely doesn't exist, so just default to none. So this will help me satisfy that, right? Whenever I basically hit the end of my linked list, return none. And now I need another base case. I know over time I'm going to decrement my index, so I'm going to check here if my index is equal to 0. If my index is equal to 0, then I could return this node right now. So just return head.val. Nice. Now that we have our base cases, we can lay down our recursive case. So if I call getNodeValue on head.next, what I can also do is pass along one less for the index, right? And I know that this recursive call is going to return me a value. I just want to pass that back up the stack, right? So if we kind of think about what's going to happen here, maybe I'll spread this a little bit like that. We know that if we were tracing through this example, when we have our top level call on the A node, we know that its index passing would be 2, quite literally from this call. And then when we get to B, it'll have an index of 1. When we get to C, we would have decremented it to 0, which means we should return it. So we're kind of going backwards here. I think with that, let's go ahead and test out this recursive version. We know that this would have an O of n time and space complexity, like we mentioned in the walkthrough. Nice. And I think at this point, let's go ahead and implement this iteratively as well, which would have a better space complexity. So iterative translations, pretty much the same code we always write for our singly linked lists. So I'll start by creating my current variable, set equal to the head. And here, I'll just lay down the foundational code for just traversing through a linked list, right? So while my current is not none, so while I need to actually keep on looking through the linked lists, I can set current equal to current.next. And as I do that, I actually want to maintain some count. So I'll say count equals 0. And over time, I should be incrementing this count. So maybe at the end, right before I set current equal to current next, I can do count plus equals 1. So this time I'm counting up to my index instead of just decrementing my index. And I know once I hit some iteration where my count is equal to my index, then I should return this node's value. So I can just return current.val. Nice. And one thing we'll need to satisfy is, let's say that this condition is never met. That means that our index was too large, right? It was out of bounds. So like we said, we should just return none in that scenario, right? So if I ever hit the very tail of the linked list, we'll just default by returning none to satisfy an example like this one, by returning index 7 of a linked list that only has 4 nodes. So let's give this iterative version a test run here. And this should have a linear time and O of 1 space complexity. Nice, there we have it. All right, programmers, so that's all I got for this get node value problem. Practice both of these solutions, and I'll catch you in the next one. Hey programmers, welcome back. Right now, let's go over an approach we can use for this reverse list problem. So in this problem, we're going to take in a linked list as input. What we want to do here is actually reverse the order of the nodes in this linked list. So if our input list contains the values A, B, C, D, in place, meaning we want to mutate the existing linked list, in place we want to actually change the order to D, C, B, A, just ending up with the linked list in reverse order. And in this function, what we should do is also return the new head of the linked list. So technically your function for this input should return the D node. So let's come up with a strategy we can use to solve this one. When it comes to the tools we can use for a linked list, we know more or less we always have to iterate or traverse through the entire linked list. And we know that that requires at least one pointer. Typically we call it current. The trick here is to actually use multiple variables. So let's say I began my classic current pointer pointing at the head of the linked list. What I'll also need is to track the previous node I visited. At the start, because I haven't visited any other nodes, we can make this previous pointer point to null. And we know this entire time, if I have access to current, I also have access to the next node in the list, right? By just accessing current.next. We're just going to label that as a temporary variable here, and we'll call it next, and you'll see why in a little bit. So I know I need to have the long-term effect of just reversing all of the next pointers in this linked list. In other words, I need to make A point to null. And so what I can do is literally just set current.next, in other words, setting the arrow to point to previous, ending up with this. Now it should be abundantly clear why we save the B node with that next variable. Because once we reroute currents.next to point to null, we would lose access if we didn't have that next variable. And so what I can do now is shift my point of view. I can set my current to be the next and set my previous to be the old current. Just shifting my point of view like this. And now I can set current.next to be the previous node once again, rerouting this pointer. And this process continues. As we get toward the end of the linked list, what we have to also remember is technically since D is the old tail of the linked list, this entire time it actually did have a next pointer. It just happened to point to null. And so at this point, I can actually continue my general algorithm, right? I still set current.next to my previous, rerouting this pointer, and I can actually continue one more iteration. If I set current to be the next, it's now the case that current is actually at null, which means we hit the end of our linked list and we can stop our algorithm. If we look at the current state of our linked list, it is in reverse order, right? D points to C, points to B, points to A, points to null. So things are good to go there. And if I wanted to return the new head of the linked list, I can simply return the final value of the previous variable. So that actually works out pretty elegant. If we do the analysis for this algorithm, if we implement this in an iterative way, and we say n is the number of nodes, we know that the runtime is just going to be O of n, really just traversing through the entire linked list once. We can say that the space complexity is constant because we only need a fixed number of variables. So overall, this is a maximally efficient algorithm to reverse a linked list. When we go on to the code walkthrough for this, I'll actually show you how to implement this iteratively and recursively, bearing in mind that the recursive would actually suffer a slightly worse space complexity. But before we get there, try to give this a shot on your own, implement this, and if you get stuck, I'll catch you in the walkthrough video. See you there. Hey programmers, Alvin here. Right now, let's go over a Python solution for this reverse list problem. So we'll start by attacking this one iteratively. We're just going to go through the exact strategy we spoke about in the approach video. So we'll start by initializing our current variable. We'll set it to the head, and we'll lay down our foundational code for just traversing through an entire linked list. So in general, I always write my loop as while current is not none. And if I just lay down the standard code, it would look something like this, right? Keep setting current to be current.next. But now we need to work in the logic that's specific to this problem. We know that the strategy here is to create some previous variable as well, and we're going to initialize that to none. And none is a great default value for this variable because we know when it comes to the original head node of the linked list, like this A node, we know that in the output, A's next needs to become none, right? And so if I actually initialize this previous variable to be none, then I start my code by setting current.next to be previous, that will actually make the arrow point in the other direction to that previous node. So this would correctly set heads next or A's next to be none. But now I need to make sure that all of these pointers are correct in the while loop. And so before I actually overwrite current.next with the previous, what I need to do is also save the next. Because if I just overwrite current.next, I might lose access to the B node, right? Now that I have current.next saved to this variable, I can reassign current.next without repercussion. Then I can progress to the next node sequentially by simply setting current equal to next. Not only do I want to move my current to the next node, but I should also change the point of view for my previous variable. So here I should set previous equal to my current. that's basically shifting my point of view, right? So let's say we had this scenario. Maybe I'll write this in a comment. It's very easy to get lost in all these pointers here. So I have A, B, C, and so on, we'll say. And so I know I have previous equal to like none at the start. I'll just use capital N for that. And in terms of how I have these variables laid out, as soon as I enter the while loop, I know that my current is going to be the A node. I know that next is going to be the B node. And I know that previous is going to be none right now. So we'll have it aligned something like this. And I start by saving current.next into this next variable, so that's good to go. Then I set current.next equal to the previous. Current.next is represented by this arrow here. So I would actually point this arrow backwards now, right? Pointing it to just the previous node like that. And at that point, I've actually killed this arrow. So this arrow is no longer. And so I've just completed line 11, and now I can set my previous to be whatever the current is. So that will have the effect of doing this. And now finally, I can update current to be what next is. So now current is over here. Now it's a business as usual. I know that if current is this B node, that means that the new next would be the C node. And that looks like it's good to go for another iteration. Perfect. Something we mentioned in our approach is once you actually hit the very end of your linked list, that is when current is none, you can return previous, because previous is guaranteed to be the new head of the linked list. So we'll go ahead and give this a shot. And this should run in O of n time and use a constant amount of space. Awesome, there we have it. While we're here, I'll also show you the recursive implementation of this. It's a little shorter, although we know that it has slightly more space complexity due to the call stack. So it's really just going to be the same premise, right? I need access to my current node, we'll call it head recursively, and I'll also need access to my previous node. I'll give it as an argument, and I'll default it to none. So if you're unfamiliar in Python, I can just have default arguments like this, right? So if someone does not pass in a second argument when they call reverse list, then by default, I'm going to make it none. And I can have my base case. So if, let's say, head is none, then I'm basically done with my traversal, and I can just return previous. That much, that is my base case, is very similar to the logic we had to finish our iterative reverse list. And so what I'm going to do is just try my best to translate this iterative code into its recursive version. So I can start by saving a reference to head.next, right? Because I'm going to overwrite head.next to point to the previous. And once I do that, that would actually, reassign the direction of the arrow. And I can just recursively call reverse list on the remainder of the linked list. So I would just reference the old next variable I have here. And I also need to be sure to pass in two arguments, right? Where the second argument would be the previous. And that should be taken as the current head. So notice how similar this code is to our iterative code. Basically, you just turned head into current, right, as the analog here. And I know that when I bottom out at the very, very tail of the linked list, or the old tail, that is, I'm going to return that tail because it becomes a new head, right? I want to make sure I pass that all the way back up. So I know this call is going to return that node. I'm just going to return it all the way back up to the top level caller. So let's give this a run. Notice how short the recursive code is, although we know it has a slightly worse space complexity. Awesome. So what I want you to do is definitely practice both of these solutions, and then you can pick a favorite and always have one of them in your back pocket. Because this problem, believe it or not, of just reversing a linked list in place is actually a very, very common interview problem. So practice this, and I'll see you in the next one.
And that wraps up the course. We solved a bunch of linked list problems. Hopefully now you're feeling good about the topic and have confidence in approaching these kind of problems. That being said, the learning doesn't stop here. You probably want to practice solving even more problems. If you like my teaching style, you should check out my full course at structy.net. There you can practice more linked list problems with me and even learn about other DSA topics like trees, graphs, dynamic programming, and more. You can try the course for free. I'll leave a link in the video description. Thanks for watching, and I'll see you next time.